All right, number 11 is a classic. A lot of these optimizations are classic type problems. Inscribing shapes or superscribing shapes around shapes that are inscribed is a favorite hobby of math question writers. Okay, so here it says to find the volume of the largest cone that can be inscribed inside of a sphere of radius 5. All right, so imagine you have a sphere and its radius is 5. It could be 5 inches, or if you have a big imagination, it could be 5 miles. Okay, but you have a sphere, and inside that sphere, you're going to put a cone, but not any cone. You're going to put the cone that has the most volume in it. You want to know what the volume of that cone is going to end up being. All right, so step one, let's draw a picture. There's a two-dimensional circle with a center, and its radius is 5. Now, all you got to do to make it look spherish is do some little artistic rendition, of which I have zero talent. But there you go. Okay, that looks really bad, right? This looks like a freckled circle. Thank you, very kind. Maybe I'll trace out what I was trying to do here. It has one of those, one of those, one of those, one of those. Bless you. Anyway, now it's a sphere, and the radius is 5. Got it? You know what? I'm going to get rid of all that because it just obscures the picture, but I'm not going to get rid of it yet. The first thing I'm going to do before I get rid of it is draw inside there a cone. Right? Like an ice cream cone, but without ice cream. It's a lot healthier. If you draw it, it's going to look like this, and of course the cone would have that 3D effect going on the bottom as well. It looks something like that and something like that. All right? So we want to know what is the volume of this cone that is going to be the absolute biggest volume. Now, I think you could pretty much all agree that the biggest cone is going to have its vertices on the edge of the sphere, yeah? Because without that, it hasn't been stretched to its capacity. But it could be a sphere that's way up here, right? Kind of short and squatty, or it could be one that's really, really tall and narrow at the base. So once you realize the three-dimensional thing that's going on, it's probably easier just to work with the two-dimensional rendition of it. So there is a cross-section, and here is a cross-section. All right? And the radius of the sphere, I'm going to go ahead and draw the radius of the sphere instead of just going arbitrarily out. I'm going to draw it going right there. Okay, so for optimization, we drew the picture. We have the radius of the sphere. We want to write an equation for the quantity to be optimized. We're trying to optimize the what? The volume. And we're trying to maximize or minimize it? Maximize, right? Largest volume. That's how you know it's optimization. So I'm going to use V for volume. The volume of a right circular cone is one you should have memorized. What is it? Yeah, pi r squared h is the cylinder. And then all you got to do is get rid of 2/3 of it and keep 1/3. Yeah. If you take a cylinder and you get rid of all the parts of the cylinder that aren't conical, you're left with 1/3 of it. So it's pi thirds r squared h. That's the volume of a cone, and you should know that. All right, are we ready to take the derivative, or do we have a problem? We have a slight problem here. We have the volume in terms of r and h, and we want it to be exclusively in terms of r or h, but not both. It doesn't matter which one. So the constraint is the sphere. Would you agree? And the only thing that we have related to the sphere is its radius of 5. I need to somehow relate the radius of 5 to some other quantity in here. Times height? Yeah, your maximum height could be 10. So here's what you want to realize, first of all. The radius that you're talking about, little r, is not 5. That's the radius of the sphere. The radius that you're talking about is this here. That's what we're going to call little r. The height that we're talking about is that whole distance there. Now here is a magical trick for any type of geometry problem. It's always best to label the small parts rather than the big parts. Because if you label small parts, you can always build them up by addition or maybe even multiplication. Whereas if you label large parts and you try to make them smaller, now you're going to have subtraction or division. And generally, it's easier to add and multiply than it is to subtract and divide. So while this entire purple thing here is the h in the equation, what I'm going to do is call this piece right here y. And of course, this piece right here I can call 5, because that's what it is, right? So what I'm going to do then is let my height equal y plus 5. Are you okay with that? 5 is already part of the height. So what y is going to end up being then is it's going to be the directed distance above or below the center of the circle that I need to go to get the last part of the height. Okay? If y is positive, I'm going to go down. If y is negative, I could retreat up and have that little short squatty one. But by labeling it like that, notice what emerges. What emerges is a right triangle with all three sides now as single quantities, right? R, y, and 5. Now, you didn't have to call that y. If you wanted to, you could call the whole thing h, and you can let this little piece here be h minus 5. But then you have a binomial as a little part of the term. So what's going to relate y to r to 5 now in a right triangle? Pythagorean theorem. Yeah. So by the Pythagorean theorem, we know that r squared plus y squared equals 5 squared. And if you want, you can make your volume, before you get to the plug-in, you can make it, instead of h, you can make it y plus 5. All right, so now we have a function for the volume in terms of r and our y, which we have labeled, and we have a relation over here involving the constraint of 5, relating the two variables r and y. We could solve for any variable we want, so long as our primary equation for volume is in terms of one variable, either r or y. What's the easiest thing to solve for in our Pythagorean theorem so that we can plug it in? If I solve for y, I'm only going to plug it in here, but it's going to involve a radical. Y would be a radical, yucky, yucky, gross, gross. What if I just solve for r squared? Would that be cool? That'd be easier. Yeah, if you solve for r, that's fine. It's going to be a radical. When you plug it in, you're squaring it immediately. So in this case, you could just solve for r squared. And you get 25 minus y squared. So now let's plug that in right there. And you get the volume is pi thirds times 25 minus y squared times y plus 5, or 5 plus y. There is your volume. Now, let's come up with a reasonable domain. That is, what can y be? What is the smallest y could be? Well, what's the biggest y could be? Let's do that first. 5, right? If y is just going to be the distance I go past the center, I have 5 in the top, and if I go another 5, that's the whole diameter. So 5 is the biggest. Now, you can almost make a claim that you can put a bracket there. What would happen to the volume, though, as, oops, I lost my picture. As y gets bigger and bigger, approaching 5, your triangle and your cone are getting narrower and narrower and narrower, approaching a volume of 0. So you know that when it's 5, you know the volume of 5 is going to be 0. What would be the minimum value then? Negative 5. Good. Because it's the directed distance. As you let y be negative, now you're letting it approach the top. And that's making the height of your triangle and cone approach 0 as the base gets wider. And therefore, you can actually make the argument that when you let it equal negative 5, you should end up with a volume of what? You should end up with a volume of 0 again. So for the geometric shapes, when you allow the input variable that you have to be the extremes on either end, it collapses the structure down geometrically in the 2 dimensions, which should give you minimum values. And therefore, we know that for a continuous function, this is just a cubic polynomial, right? If it starts at 0 and ends at 0, assuming that they're positive in between, which they should be because volume is positive, something's going to have to go up and come back down. And by what theorem will there be then a absolute max or local max on that interval. Or an extension of Rolle's theorem. Good. Yeah. Rolle's theorem, which is, of course, a specific IVT. Okay, cool. So now we just need to take the derivative and set it equal to 0. You want to expand first, or you just want to take the derivative using the product rule? I would recommend the product rule. Yeah. So let's do that one together, because this is the one that people still tend to mess up. Pi thirds is just a constant multiple. It's going to go along for the ride. But I'm going to keep it way out. Because remember, when you do the product rule, you generate two terms. I'm going to leave pi thirds out front of the whole thing. So now the derivative of the first factor with respect to y. Y is our independent variable, so it's just negative 2y. We don't put dy dx here because we're not doing it implicitly. We're taking the derivative of v with respect to y. So you get negative 2y times y plus 5, and then plus 25 minus y squared times the derivative of y plus 5 with respect to y is 1. So there it is. And now we can set it equal to 0. As soon as you set it equal to 0, you can abandon the v prime. All right, so here's what I'm going to do. I want it to be factored completely. So I know that I can leave this first one alone, and I'm going to call y plus 5. I'm actually going to call it 5 plus y. Are you okay with that? All right, in the second one, 25 minus y squared, that's the difference of squares. That factors into 5 minus y times 5 plus y. And now it's equal to 0. By factoring each term, I now have a common factor that I can factor out. So rather than expand the whole thing and then try to refactor it as a cubic, or it'd be as a quadratic, I'm going to just use the factoring that's already kind of built in. And so now I'm going to factor out the 5 plus y, and I'm going to be left with a negative 2y plus a 5 minus y. And that's equal to 0. And I can just tidy it up one more time, because now I have three factors. Pi thirds, 5 plus y, and then the second one ends up being 5 minus 3y. And now you can set them each equal to 0, which means y equals negative 5, or y equals 5 thirds. Well, what do we know about y equaling negative 5? I got two critical values now. Which one is going to maximize the volume? Yeah, 5 thirds, because we've already talked about negative 5. That minimizes the volume. It makes it 0. So we know that that's going to be the answer. Okay? Or that's going to be the quantity that I should say maximizes the volume of the cone. Now we do need to answer the question. We are after the volume of the largest cone. The volume. So if you want, you could find the height and then plug it back into the original Pythagorean r squared h. But remember, right here, before we took the derivative, there's the entire volume now in terms of our optimal value that we found. Why? So, answering the question, we'll say the max volume is, and I'll just plug it in, pi thirds times 25 minus 5 thirds quantity squared is 25 ninths. That saves a little bit of parentheses. Times 5 thirds plus 5. And I'll just keep that as an exact answer. And since we don't know what the units of 5 were, it would just be cubic units. And you don't even have to put that. But it would be cubic units, cubic feet, cubic inches, whatever. All right, so the key on this one was the Pythagorean theorem. The key was the Pythagorean theorem. So whether you label the small part as y or you label it as h minus 5, it's up to you. If you did have it as h minus 5, you're going to have a binomial squared in the Pythagorean theorem. But the key was the Pythagorean theorem, which meant that you're going to create this little right triangle. So there is one in the worksheet, and here's kind of a heads up. The one in the worksheet has a cylinder instead of a cone, and you're trying to find the maximum whatever. Here's what it's going to come down to. Do the two-dimensional depiction. That's going to be essentially a rectangle inside of a circle. And the volume of a cylinder is pi r squared h. Pi r squared h. So here's what you want to do. call this distance, call it y, and call that y. Because it doesn't go all the way to the top. It goes symmetrically above and below the center. And then you can call this the radius of the cylinder. And then, of course, that right there, I'm going to call it big R. That's the radius of the sphere. So you can still get your little quadratic, or I'm sorry, your Pythagorean theorem right there. The height of the cylinder is going to be 2y instead of 5 plus y like it was in the last one. So very, very similar type of calculation, all right? So there's the insight into the cone. So whether it's a cone, there's the insight into both, actually, the cone and the cylinder. It's all about, when you're doing these inscribed, it's all about the Pythagorean theorem. That's going to get your constraint equation. All right. Any comments or questions about that? Was that fun? It's fun to put things inside of other things, like a teddy bear inside of a balloon. I saw that for the first time when I was like 4, and I freaked out. How did they get the teddy bear inside the inflatable balloon? I still don't know to this day. But it was in there. It was like in a bouquet. So anyway, I guess the bear was just born there. That's the answer that I've come up with. Okay, a Norman window. Yeah, what's a Norman window? That thing. It's an archtop window, molded as a single unit together. So an archtop window is being built whose bottom is a rectangle and the top is a semicircle. If there are 12 meters of framing materials, what's the width of the window that lets in the most light? Okay, how do you know that this is an optimization question? Most. So what are we trying to maximize? Light. How do you maximize light? Yes, surface area, right. Assuming that the sun is turned on, right? Don't build this in the shade. You want to maximize light by building it, out in the open on a sunny day. But yeah, the window that's going to let in the most light is the one that has the largest surface area, largest area. All right, so step 1, we need to partition this up. So I'm going to use the outside to make my marks. Now, in the spirit, as I said in the previous problem, of assigning variables to small things and building up rather than big things and working down, I know that the critical measurement for a circle or a semicircle is its radius. So I'm going to let this be the radius, little r. Now, once I have that as the radius, I don't need to call the width of the window w. I don't need to introduce another variable, do I? Because what is it? 2r. Yeah. Now, notice if you wanted to call the width of the window w, now you're going to have to call your radius w halves. You're working with fractions. Yucky, yucky, gross, gross. Or embrace them. I don't care. So I've got r and 2r. Now, there is one other thing that I need to come up with. I don't know what that is. I'm going to call that h. I do know that the overall height of the window, maybe I'll call it y. If you call it h, you might think it's the height of the window, but it's not. It's part of the height of the window. The actual height of the window is, if I have labeled it like this now, the actual height of the window is y plus r. And the width of the window is 2r. So there you go. Labeling small parts and building up rather than big parts and having to scale them back. You don't have negative signs or division signs. All right, so the first thing we do once we've labeled it is we write an equation now using our variables, our setup, for the quantity we're trying to maximize. We're trying to maximize the area. Maximize the area. So I'll use A for area. It's going to be made up of 2 parts, the rectangular base and the semicircular top piece. And we'll add them together. So what's the area of the rectangular base? Y times 2r, yeah, or 2ry. 2ry plus the area of a semicircle is the area of a circle divided by 2, right? The area of a circle is pi r squared. So half of that would be pi halves r squared. It's easier to pull the half out front with the pi and call it the coefficient. So pi r squared divided by 2 is the same as pi halves r squared. So there's your rectangular base plus the semicircular top. Yes? Okay, great. So I have my equation for the area, but it's in terms of both r and y. And I want it to be in terms of r or in terms of y, but not both. So what's my constraint? What's preventing me from making this window infinitely large? It has to have 12 feet of framing material. So we'll just assume that that is the perimeter all the way around the window. All the way around the window. So 12 all the way around the window should be, how many Ys would I have? 2 Ys, okay, for the stiles we call them. 2Y, plus I have a 2R for the width for the bottom rail. And let's assume we don't need a rail at the top. We just now have the last little piece, which is the semi-circumference. Good. Half of the circumference. Pi r. Good. The circumference is 2 pi r. Half of 2 pi r is 1 pi r. So there it is. 12 equals 2y plus 2r plus pi r. You want to solve that for r or y? I'd rather solve it for y looking into what I have to do with it, right? If I solve it for y, there's only one place to plug in. If I did solve for r, I have to plug it in twice and square it once. No, thank you. Now, 2r and pi r are like terms in the sense that they have both r in them, but they have unlike coefficients. So at this point, if you wanted to factor out the r and say that you had a compound coefficient of 2 plus pi, you can drag around a 2 plus pi with you the whole time. I am not going to do that. Okay, it gets a little bit too confusing. So I'm just going to leave it like this. I'm just going to solve it for, I'll solve it for, what do we say, y? Yeah, so 2y is going to equal 12 minus 2r minus pi r, and then I divide through by 2. Y is equal to, let's see, half of 12 is 6, half of 2 is 1, half of pi is pi halves. So I just distributed 1/2 all the way through. You okay with that? Distributed 1/2 all the way through. All right, so here now I have y in terms of r. Now I can plug that right into here. So the area is going to equal 2r times 6 minus r minus pi halves r plus pi halves r squared. And now you have the area in terms of r. So let's think about the lower and upper bound for r. What would be the smallest r could be? 0. If r is 0, what happens to my window? Yeah, there's no light. It's called a wall, right? Now, again, if you want to think about it because it's a geometric shape, if r is equal to 0, that should minimize the light, right? That's going to be an absolute min on my interval because I won't have a window. What's the largest r could be? That would be a little bit harder to come by. So here's what I know. It's not real critical to come up with an upper bound. Just know that the radius has to be positive. How about that? We did that in the beginning. And I know that 0 is not going to work. Okay, so now I can find the derivative. I'm going to clean this up a little bit first. I'm going to go ahead and distribute the 2r. So I get 12r minus 2r squared minus pi halves r squared plus, oops, I'm sorry, that's plus pi. The 2 divides out. So that'd be a minus pi r squared plus pi halves r squared. Now notice you have 3 r squared terms. 2 of them have pi in it. So I think I'll combine those and leave the 2 by itself. So 12r minus 2r squared, that ends up being minus pi halves r squared. Now again, what do you notice about the graph of the area in terms of r? It's an r squared, so it's a quadratic. Your leading coefficient is -2 minus pi halves, which is negative, right? So again, this thing opens down. If it's a parabola that opens down, you know for sure that the local max location is also the absolute max location. So we're heading in the right direction. I just need to take the derivative and set it equal to 0. So the derivative of a with respect to r is 12 minus 4r minus pi r. And if you set that equal to 0, I will say 12 equals 4r plus pi r. And if you factor out the r and divide through, you get r is equal to 12 over 4 plus pi. And that would be in units of length, which is meters. So I know that that's going to be the radius that maximizes the area. And of course, could that actual ideal window be built? It can't actually be built because pi is an irrational number, but we can get something that's pretty close. All right, so now to answer the question, what is the width of the window that lets in the most light? So what do we say the width was? 2r. So, comma, the ideal width, I'll say, is 2 times that, which is 24 over 4 plus pi meters. Now, here's a follow-up question. What is the overall height? The overall optimal height. I shouldn't say the ideal width. I should say the optimal width. That's better. That's a lot better. Some people may hate the sunlight, and that wouldn't be ideal for them. The optimal width is that. What is the overall optimal height? Take a second and find that on your own. You know that h is equal to y plus r. That's a little bit more interesting question. It helps if you use the right numbers. All right. Did y'all come up with a nice cleaned up answer? If you let height equal the y plus r, and you plug in what y is, we already said y is 6 minus r minus pi halves r. That's from this right here, our constraint, plus r. This r and this r here cancel. So this one and this one cancel. So you're just left with 6 minus pi halves r. If you then plug in the r that we found to be the optimal r is 12 over 4 plus pi, this would be an answer right here. But if you keep working at it to get it looking in the same form, 12 halves is 6 pi, so you get 6 minus 6 pi over 4 plus pi. To get a common denominator, multiply 6 by 4 plus pi over 4 plus pi, and now you can combine them over the same denominator. If you distribute, then you get 24 plus 6 pi minus 6 pi over 4 plus pi, and now your 6 pi's cancel, and you're left with 24 over 4 plus pi. So if that's the optimal overall height, and the optimal overall width was the same, then it turns out that the optimal Norman window would fit inside, wait for it, Colin, what type of opening? A square opening. Yeah. Yeah. And that's not necessarily intuitive because this whole thing is not just a rectangle itself. It's a rectangle with a semicircle. So it would fit inside of a squared opening. Okay? Pretty interesting. All right, so the Norman window problem ended up being just a little quadratic. That's all it was. But you had unlike coefficients, so it's easier, in my experience, just to treat them as two separate terms rather than carrying around a compound coefficient. All right, last one. This one's going to be anticlimactic. It's going to be pretty easy, but it does show up sometimes. Find an equation in general form, okay, for the tangent line to the graph of this cubic polynomial that has a maximum slope. I want to make my tangent line have the maximum slope. So it is optimization. First thing I need to do is maximize slope. Well, I need to come up with a slope equation. How do I get a slope equation from the y value equation? The derivative. Yeah. So let me call this capital S for slope of x. The slope function is going to be really f prime of x, which is going to be negative 2 minus 2x minus x squared. So now I want to maximize f prime. I want to maximize s. Alrighty, how am I going to do that? Well, I know that this is a parabola that opens down, so I know that there is going to be a maximum. Maximums for any function can occur at critical values, right? So now I need the critical values of my slope function. So s prime of x, which ends up being f double prime of x, is equal to negative 2 minus 2x. We then set it equal to 0, and we get x is equal to negative 1. So this is my critical value of my slope function, or f prime, bless you. Now again, because my slope function was a parabola that opens down, I know that this critical value is going to be the location of its absolute maximum, right? So now I can find the maximum slope. So the maximum slope of f of x is my slope function evaluated at negative 1, which is also f prime a negative 1, which is what? What do I get when I plug in a negative 1 into f prime? I get a negative 2 plus 2, that's 0, minus negative 1 squared is 1, so I get minus 1. How can it be that negative 1 is the biggest slope? Yeah, if the biggest slope is negative 1, that means all the slopes are less than that, which means they're all negative, right? That means our function has to be monotonic what? Decreasing. And the slope is maximum at negative 1. That's going to actually be where the graph is the least steep, right? That's where it's the least steep. So our function is pretty steep, and then it goes like that, and then it goes like that. And right here, where the slope was at a 45 degree, where the slope was negative 1, that's where the slope was the greatest. All right, so now that I have my value for the maximum slope, I can write the equation of the tangent line. So now I want the equation of the tangent line at the point negative 1 comma something. I know the slope I just found to be negative 1, which happens to be the same as the x value. How do I find the y value there? Plug it into f of x. Okay, let's do that. Now, if I plug in a 1 for x, I get 2/3 in the front minus 1/3 in the back. That's 1/3. Actually, it's negative, yeah. F of negative 1. I get 2/3 plus 1/3, which makes it 3/3 or 1. So I get 1 plus 2 minus 1. That gives me 2. Right? So the point is negative 1 comma 2. And now that I have all my ingredients right out in front of me, the x value where the slope was the maximum, the y value where the slope was the maximum, and the maximum slope itself, I can get the equation to be, in Taylor form, y equals the y value of 2 plus the slope, -1, times x minus -1 or x plus 1. Now, it did say to put it in general form. So remember, general form is of the form ax plus by equals c, and typically a, b, and c are all integers. So if you have a fraction, you eradicate it. We're not going to have a fraction, so all we have to do is just distribute, and then bring the x across, and you get x plus y equals 2 minus 1 is 1. And there it is. All right, so what gets students on this is it's actually pretty easy. You don't have to write your own equation. You have the equation given to you. You do have to find an equation, and that's the derivative. So people always ask, why are you taking the second derivative of that? Well, the answer is because we're trying to maximize the slope function, which is f prime. So f prime is our starting point, and now I need to find its critical values by taking its derivative. All right? So that's why if you need to call it something temporary like s of x or slope of x, I need to maximize my slope function s of x by finding its derivative. But then in the end, you really have three equations. You have f double prime that you're setting equal to get your critical value. You have f prime, which you plug back in to get your maximum slope. And then you have the original f of x that you're plugging into to get your original y value. So even though it's an easy little polynomial question, there is a lot to keep track of there. All right, and that takes care of optimization. Usually that's going to be given to you like in a hint. I think there's a couple of questions on there that say, what is the maximum value of the slope? And the slope is like either in bold or italicized. So that's just a reminder that you need to maximize the slope by finding its critical value. So you will need f double prime for that. All right, and there is a genius question at the end, which doesn't mean optional. It's a good one, all right? So if you haven't looked at it yet, here's essentially what it says. You have a piece of very, very expensive material, okay? Titanium, platinum, copper, deluxe, whatever. You don't have enough to do trial and error. But what you're really desiring, you're after a cone, right? And what you're going to do is you're going to bring the edges together, right? So, and then this is going to be some type of like a solder. So you're not going to overlap it to rivet it together or anything. They're just going to come neatly together, and that's going to make a cone. You want to maximize the volume of the cone. Now that line right there ends up being this line here. When you cut out a sector of that tin and you bring these two then edges together that are highlighted, if you bring those two together, this thing will buckle up, and now you're staring at the top of the cone at the center of that circle. And you want to know then essentially what angle do you need to cut out from your expensive piece of material so that you maximize the volume. And it's kind of a fun question, so maybe like don't look at the answer choices right away, but here's what you're going to need. The perimeter of your cone. The perimeter of your cone is going to be this right here. Correct? Okay, when you bring it together. So let's call that the perimeter P. It's going to be the entire circumference. Let's say that this it had a radius r. The entire circumference of a circle is 2 pi r, yes? And then you're going to subtract from it this right here, which remember is the arc length. You remember the formula for arc length? It's r theta. Where theta is in what? Radians. Yeah. The arc length is r theta. So that perimeter is over here now. And if you let maybe I should let this equal big R. Let me do that. I think I give you the value of it. But let's say it's big R. And we'll say big R is a constant. You actually have to let big R be a constant. What's the variable R is this over here. The radius of your cone. So the bottom of the cone ends up being the circumference. So 2 pi r, 2 pi little r, is the base, and that should equal what? 2 pi big R minus big R theta. So that's a way to relate your little radius of your resultant cone to the angle theta that you're cutting out. Big R is a constant. Well, let's just call this height. And, of course, the volume of the cone then, and the time that remains, we have plenty of time. What's the formula for the volume of a cone? Second time today. Pi thirds R squared H. So what you're trying to do, you're trying to get ultimately your volume as a function of theta. That's what you're shooting for. It's your goal. Well, notice you're pretty much there. You've got, if you solve this for little r, you get little r is 2 pi big R minus big R theta over 2 pi. Remember, big R is a constant. So you got little r in terms of theta. You just need to get the height in terms of theta. How are you going to get the height in terms of theta? Pythagorean Theorem, good. Because the height of the cone is little h, the radius of the cone is little r. Well, what's the hypotenuse, so the slant height? It should be big R, right? If you said that, I didn't hear it. I'm sorry. Yeah. If you bring these two together, the radius of the sphere ends up being the slant height right here. And so now, by the Pythagorean theorem, you have big R squared, big R is a constant, equals h squared plus r squared. And of course, you could do what? You could solve that for h. It's equal to the square root of r squared minus r squared. And now, since you can write h in terms of little r, and you can write little r in terms of theta, you can now write h in terms of theta, and then you can plug both of them in here. So that's where you're going to be going. And then you get this ugly volume formula in terms of theta. I say on the notes that you don't have to take the derivative and set it equal to 0. You could just graph the volume as a function of theta in radians, and then use the calculator's graphing capability to find the max. Okay? So there's kind of the game plan for that problem. But it's a good one. So when you're bored and you're done, pay a little more attention to that one right there. What would be nice is if you could do this in terms of big R, then for any size disk, you would know exactly how much to cut out to get the maximum volume on the cone. Question, Tyler? No? You got all that? Yeah, okay. A little tired? Dilly. Yeah. Too much turkey for breakfast? The tryptophan hitting in? Boom. All right. Okay, we're done. We are done.